In this session, let's start looking at multiple regression, wherein the intention is taking two or more independent variables. So I try to find out the relationship between the dependent variable and two or more independent variables. So typically if I assume y is my dependent variable and x1 and x2 are two independent variables. So when I am trying to build a relation like y equal to b0 plus b1 times x1 plus b2 times x2 plus so on bn times xn plus some error component epsilon. This kind of a relationship that we are trying to build between the independent variables and the dependent variable is called as the multiple regression kind of a relation. And typically in this multiple regression, it's an extension to the simple regression kind of a mechanism where we had only one independent variable to be considered. So the same thing I would like to take up a small example, and based on that data set we will try to see how that multiple regression can be applied. Just like the way we have discussed in case of simple regression, the intention of deriving these values b0, b1, b2, which are the coefficients of the various variables x1, x2 and so on, is with an intention of mitigating this error. So if I assume that this is the actual value and this is my predicted value, the difference between the actual and the predicted, the square of it, which is what is nothing but the error squared. This has to be minimum, and whatever the choice of or combinations of b0, b1, b2 are chosen from this perspective of minimizing this error is what goes as the best fitting multiple regression model. So the way we execute it is more or less similar to that of a simple linear regression kind of a model itself. Specific tools can also generate, specific tools like Excel can also generate the multiple regression analysis. So the first thing is, let me try to take one data set, and based on that data set I would like to work out or interpret the various items that are coming out of the multiple regression model. So let me take a data set. Yeah, this is the data. So this is the data set where I am having three specific variables for the various pharmaceutical companies. The profits as of today for this quarter, the revenues of this quarter which is under the sales, and the total assets which the company has. Now I would like to know, is there any way I can predict the profits of these companies the moment I know what are their sales and what are their assets? In the simple linear regression model we have looked at finding out, based on the sales, can I predict the profits of the company? But now, based on sales and assets, two variables, I am deciding two of them as independent variables. Based on the sales as well as assets of each of these companies, can I predict the profits? So that kind of a model which we are trying to build is what is a multiple regression model, because I am going ahead with two independent inputs or two independent variables in this process. So let me just quickly execute the multiple regression model, right, and after that we'll get into the interpretation aspect of that. So in the regression part, okay, I'll look at the input variable is the profits. Profits form the input variable y, right? And whereas the independent variables, here I am considering two. Anything above 1, we call it as a multiple regression model. So I will consider the sales as well as assets, two of those variables. And when I am trying to do some kind of regression analysis on the top of them, these are what are the values that are coming up. So I need to have a mechanism to interpret these values, right? Okay, let's look at what is the output that this regression model has generated. We have gone ahead with 97 data points here. That is one thing which we can directly make out. We have taken a sample size of 97 to perform this particular analysis, and logically looking at, this is what is our model. So if I have to write this particular model, this is nothing but minus 43.098, right? If at all I have to write the regression formula for this particular model, then profit is equal to minus 43.098 plus 0.14616 times sales minus 0.0064 times the assets. This is what is the formula that has come out. If at all I have to predict the profit based on this regression equation, it is working out to be this particular number. And so what are the various terms that we can interpret here? The intercept. What is the way we can define the intercept? Minus 43. If at all my independent variables are 0, for a company which has generated 0 sales and which has 0 assets, I can very well say their profit would be a minus 43 units, which means they are going to generate a loss. If the sales is not existing and the assets are 0 for that particular company, it is going to generate a profit of minus 43 units, which means it is going to generate a loss. That is how we interpret the intercept term. And let's say when I am looking at these two coefficients, which are typically B1 and B2, I call them as the partial slope coefficients. In a simple linear regression model, we used to call them as slope coefficient only. But in a multiple regression model, we call them as partial slope coefficients. The reason being, this value represents what is the increase in profit if the sales increase by $1. Sales increase by $1, the profit will increase by $0.14 provided there is no change in the assets. So keeping all other variables constant, if the sales change by $1, the profit will change by $0.14. That is what is the interpretation of the partial slope coefficient. So in this case also, it means that if at all nothing else is changing, if the assets of the company increase by $1, probably the profit of that company is decreasing by $0.0064. That is what is the negative sign indicating to us. So that is how we interpret the multiple regression equation. So now that these two values are generated, right, now that the coefficient and the partial slope coefficients are existing for us, my next objective is to test each of them for the significance. So I have to test each slope coefficient for the significance. Hypothesis testing I have to do on each of the slope coefficient. Now for that, just like in a simple regression process, my null hypothesis will go as the variables b1, b2, etc. are all zeros. Whereas my alternate coefficient says no, they are not zeros. b1 not equal to 0, b2 not equal to 0, and so on. So the multiple coefficient, each of the coefficients, it is not equal to 0, which means it is significantly different from 0. So the way we are going to work out again is I compute the t statistic value for each one of them, which the way t statistic is computed is nothing but the coefficient minus hypothesized value, because here we are looking at hypothesized values of 0 only, coefficient divided by standard error. Standard error for each of the coefficients is already computed by the regression process. So coefficient divided by the standard error gives me the t statistic. So I could have easily taken coefficient divided by the standard error giving me the t statistic. So this is what the table is also displaying to us: minus 2.06, 8.43 and minus 0.50. So these are the way the t values are typically computed for us. Now our intention is compare the t value with the critical value. And how do I look at the critical value corresponding to this? I can easily take from the t distribution table for a 5% level of significance and 96 degrees of freedom, one less than the sample size, 96 degrees of freedom. The critical value comes out to 1.984. So as long as my computed t value lies between minus 1.984 to plus 1.984, I do not reject the null hypothesis. And what is the null hypothesis for us? That variable is equal to 0. Whereas if at all I find my calculated value less than minus 1.984 or even greater than 1.984, I can reject the null hypothesis and I can very well go with the alternate hypothesis. Now here in this case, we can see that this is outside the interval, this is outside the interval, whereas this one is not outside the interval. Only for the sales the t value is outside the interval, and for the intercept the t value is outside the interval. Whereas for assets the t value is not outside, is within the minus 1.98 to plus 1.98 interval. So I can very well say that the sales, the coefficient of sales is statistically significant, but I don't have the evidence to say that the coefficient of the assets is statistically significant. So for each of them, I'll do this process wherever we are seeing that the t value is greater than the positive side of the critical value or less than the minus side of the negative, less than the negative side of the critical value, we can reject the null hypothesis and say that the value, that the coefficients are statistically significant. Even a similar kind of understanding can come out using the p values, right? When I am using the p values which are generated by the system, again it's a kind of a smallest significance level. Whatever is the p value that is computed, it's the smallest significance level where the null hypothesis can be rejected. So where the null can be rejected, so H naught is rejected. What does that mean? So in this case we have 4.2%, 0.0042. So when I convert them into percentages, this is around 4.21%. So at that smallest significance level, at the significance level of 4.21% and above, at 4.21% significance level and above, we can reject the null hypothesis. Whereas in our case we were looking at 5% significance level. So because it is above 4.21% significance level, we can very well reject the null hypothesis and go with the alternate hypothesis in case of the intercept. Same is the case with respect to sales at 0% significance level and above. So which means you can always reject the null hypothesis when it comes to sale. Whereas when it is coming to the assets at 61.4% significance level and above only, we are able to reject the null hypothesis. Which means we at 5% significance level we cannot reject the null. So when I am directly looking at the p value generated by the regression model without doing any kind of calculation, just by mere looking at the p values, we can very well make out whether this particular coefficient has to be rejected, coefficients assumption of being equal to 0 has to be rejected or failed to be rejected. So that's how directly p values help us in terms of testing for the significance of the coefficients of regression. Now sometimes we may be interested in testing out not with respect to 0, but if I want to test out whether it is equal to some other value, let's say if I want to test is the coefficient of sales equal to 0.1. So I am making a null hypothesis saying B1 equal to 0.1, whereas my alternate hypothesis will go as B1 not equal to 0.1. So in this case the t statistic is nothing but the actual coefficient 0.146 minus the hypothesized value, the actual coefficient minus the hypothesized value divided by the standard error. Minus hypothesized value is 0.1 divided by the standard error in this case is this much. So I am getting 2.66. This 2.66 is also outside 1.98 limit. So which means at 95% confidence level or at 5% significance level, I can even reject this null hypothesis of B1 equal to 0.1 I can very well make a statement that P1 is not equal to 0.1, though we have a value of 0.14. So that is how we can typically test for any other coefficients, any other value also for these coefficients, but primarily to check out whether the coefficient is statistically significant or not, we generally use this p values, and we also test out using the t, or sometimes, as we have earlier discussed, we can even use the confidence intervals also. The 95% confidence interval, whatever the system has given us here, I can very well derive those confidence intervals as we have discussed earlier also, wherein I take the coefficient minus whatever is the t value for 5% significance level multiplied by the standard error, that is the lower limit, which happens to be minus 84.61, and similarly I can take the upper limit also, wherein I can consider the coefficient plus 1.98 times the standard error. So the same logic we can use. So here in case of intercept, I am seeing that the lower limit is minus 84, the upper limit is minus 1.5, which means 0 is not present in this interval at all. So in the 95% confidence interval, 0 is not present. So that's where we are saying that the coefficient is significantly different from 0. The same logic, if I look at for the sales, I take this number minus 1.98 times the standard error, and the same thing the other side, the coefficient plus 1.98 times the standard error. So almost this is working out to this numbers. So again, 0 is not, the 95% confidence limit for this particular sales coefficient is 0.11 to 0.18. 0 is again not present in that interval. Because 0 is not contained in the interval, we can very well say that the coefficient is significant and it is very much different from 0. Whereas if you look at the assets, this minus 1.98 times the standard error is giving me the minimum value is minus 0.03, and on the other side this plus 1.98 times the standard error, this is giving me plus 0.01. So the 95% confidence limit for the assets is from minus 0.03 to plus 0.01, means there is a possibility of 0 in that interval. So wherever 0 is present in a particular interval, we are talking about that particular coefficient may not be statistically significant, whereas in other cases that particular coefficient is going to be statistically significant. And now once I know in this case, yes, the assets are not statistically significant, the coefficient of asset is not statistically significant, whereas for the sales it is statistically significant. Now that we have these variables, so generally if at all I find that the assets is not statistically significant, it is advised that I remove that assets and then rerun the regression model, which would be similar to that of sales itself. But wherever I find that even after the addition of the second variable, it is becoming more and more, even the second variable is also statistically significant, then obviously it will result in a better regression model for us, right? And now assuming that both of them are statistically significant, if at all I have to predict the dependent variable from the set of independent variables, right, for some kind of a value. If at all I want to predict, let's say I want to say for a company which is having a sales of 1000 and assets of 2000, what should be the expected profit? Then I can say minus 40 plus 0.14 times the sales minus 0.0064 times the assets. So this should be the profit that the company should expect in case the sales are 1000 and the profits and the assets are 2000. And whatever, if we are looking at some of the important aspects as a part of this linear relationship kind of a model, we see that whatever the relationship we are establishing between the dependent variable and the independent variables, that is purely a linear relationship. Whether it is in the case of simple regression or multiple regression, we say that the relationship is a linear kind of a relationship. And the independent variables, they should not be random values. Right, the independent variable, the sales as well as the assets which I have taken, they should not be random values. They are basically the real data values with respect to sales and the assets of various companies. So, I mean, I should not take the independent variables as completely random values. And yeah, this is where I would like to look at the error term. Okay, let me compute the predicted value based on our model. The predicted value goes as the intercept plus the sales coefficient times the sales value plus the assets coefficient times the asset value. Right, this is what is the formula. So this is what is coming out to be the predicted values, and based on this, if I am trying to find out the error, which is the difference between the actual profit and the predicted profits. So the error is coming out to something like this. These are the errors in various cases. Right, these are the errors in various cases. These are the profits and these are the predicted profit, computing the errors. Now when I am looking at the expected value of the errors, okay, the mean of the error, it should be 0. The determination of B1, B0 and all whatever are coming out, the mean of those error, if I try to take the average of the error term, this holds true even for a simple regression also. The average of the error term, here you see it is very close to 0. 10 to the power of minus 14, which is 0.000000, 14 zeros followed by a number. So this assumption, one of the major things that has to come out of this regression model is the mean should be 0 and the variance of the error term is constant for all the observations, and error terms are not correlated with each other. So for each of the companies, the error term is coming in a kind of a randomized fashion, and error term should be normally distributed. One more important factor for us, error term should be normally distributed. So if I look at the skewness of the error term, if it is normally distributed, the skewness of the error term is actually not 0. Look at it. The skewness of the error term is minus 2 point something. which means there should be some kind of extreme outliers that are present in our data, right? The original data itself is not so normal, so it is worth to remove a couple of values before we really look out for an advanced approach in terms of the multiple regression process. So these are some of the key assumptions that we need to be comfortable with as a part of the multiple regression process. Then, if at all I have to test the overall significance of the entire model, as we have seen earlier also, the entire model, the total goodness of fit, if at all I have to look out for goodness of fit of the model, I will depend again on the ANOVA analysis, which is more or less similar to what we have discussed in case of simple linear regression model. But before we do much more into that, we again look at the total degrees of freedom, 97 observations, so total degrees of freedom is 96. Because there are two independent variables, we take 2 as the regression degrees of freedom, 94 as the residual degrees of freedom. Then I need the total sum of squares. So the total sum of squares is the actual profits. So when I am taking the actual profit, the mean of the profits, right, mean of the profits is nothing but the average of all these numbers. This is the mean of the profits, and I also want the sum of the squares. So each profit, from each profit subtract this mean and do a square. So sum of the squares. So sum of the squares of the total sum of the squares of profits. When I am taking total sum of squares of the profits, I am looking at, I'll use this formula, sum of x minus y squared otherwise let me do it as sum of the squares of the profits. So what I can do, each value x minus x bar, probably y minus y mean square, let me do like that. So y minus y mean squared, y minus y mean squared. Okay, so this is what it is. So I can say the total sum of squares of the y minus y mean squared, which is nothing but, this is around 7.63 million, which probably if you look at here has worked out to 7.63 million. So the original data, I find the mean and then subtract the mean from each of the observations, square it and add it up. That is what will give me the total sum of squares. Then we have predicted the value using the regression equation. So again, if I say this, if I do the same thing, y1 minus y1 mean squared, y1 mean also will come to the same number. Okay, let's see the y1 mean. When I say y1 mean, it is coming out as the average of this particular number. So the y1 mean also is the same value. It will be the same always. So what I am looking at now is the sum of squares So which forms as regression sum of squares, which is coming from the predicted, which is, I will take the error. What is the error in this case? I take the predicted value minus whatever is the mean. I take the square of them. So this is the y1 minus y1 mean square, and the regression sum of squares will directly come out to the summation of these numbers, which is coming out to 4.86 million. So the regression sum of squares is coming out to 4.86 million. The remaining will become the residual sum of squares, or the other way to identify the residual sum of squares is, we already have this error. So error squared when I am doing, that is what is the residual sum of squares. The error squared, when I take the square of this error, right, the square of this error, and residual sum of squares or error sum of squares, which is coming out of the error, is nothing but the summation of these particular numbers coming out to 2.76 million. The error sum of squares is coming out to 2.76 million. Then the mean sum of squares was nothing but the total sum of squares divided by the degrees of freedom, coming out to this number. Here also 2.76 million divided by 94, coming out to 29,000. And if at all I have to test whether the model is a good fit, I will work out between these two. So the F statistic, because we are making a null hypothesis there, saying the variance of the regression sum of squares is equal to variance of the residual sum of squares, where my alternate hypothesis comes, variance of regression sum of squares is not equal to the variance of the residual sum of squares. And for that F statistic I am using, which is the variance of regression divided by the variance of residual. Instead of variance, I look at the mean sum of squares, which is a kind of a proxy to the variance. So I designed this particular number divided by this particular number, giving me 82.54. That is what is coming out as F. And again from my tables, the critical value for F, if I find out using a formula F inverse in Excel, for a 5% degrees of freedom, 5% level of significance, 2 degrees of freedom for the regression and 94 degrees of freedom for the residual, the critical value is 3.09. So as long as our calculated value of F lies between 0 to 3.09, null hypothesis is taken, means it cannot be rejected. Whereas in our case, the calculated value is 82, which is way beyond 3.09. So I will reject the null hypothesis and go with the alternate hypothesis. So in this case, my alternate hypothesis is coming out as, there is a clear-cut difference between the variance of the regression as well as residual. Means the regression model is able to explain the variance in the dependent variable quite comfortably than the error. So from that standpoint, we can very well move forward saying this particular model overall is a goodness of fitment. It can very well be used for predicting the profits, because overall there is a fitment of the model. But is the assets really required or not, because individually that particular coefficient is not statistically significant, and what should I do with that is the next thing which we are going to deal with. The next important aspect that comes in this context is the coefficient of determination, which is r squared, right? The coefficient of determination, which is r squared, which we have used even in single regression, simple regression kind of model, wherein we simply said the regression sum of squares divided by total sum of squares. Means if the total sum of squares, let's say in this data, whatever the variation from the mean I have taken for the total data, and at the same time I have taken for the predicted data. It has come out that for the total data the sum of squares is 7.6 million, and out of that 4.86 million is for the predicted. So the regression sum of squares divided by the total sum of squares is what is the value of r squared for us. So here I could have directly looked at the regression sum of squares divided by total sum of squares, which is 0.63718. This simply explains to what extent the variance of the dependent variable is explained by the independent variables, because here we have more than one independent variables. We are saying collectively, the independent variables collectively, to what extent they have explained the variation in the dependent variable. That is what we are calling as r squared. So the total regression sum of squares divided by the total sum of squares is what we are calling as coefficient of determination. And probably when we are looking at this term, especially in case of multiple regression, there is no meaning associated with correlation coefficient r. In single regression, we even found that r squared was same as the correlation squared. Whereas in case of multiple regression, we don't have any kind of interpretation associated with coefficient of correlation. These two need to be looked at as two different aspects itself. Right? So because sometimes if we are seeing here this particular even this Excel, it has given me what is called as multiple r, which is nothing but it's a square root of this particular r squared. But that is not the correlation of the independent variables together and the dependent variable. Correlation is always taken on a pairwise scenario. It's not taken collectively. There is a difference in the way the correlation is defined and coefficient of determination is defined. Coefficient of determination comes from the variation, the sum of squares of deviations from the mean for the original data versus the fitted data. So whatever extent of the variation in the original data is taken care in the fitted data is what is the extent of the coefficient of determination, which is r squared. So in this case, 63% of the variation in the original data is taken care by the regression model. Means almost 37% of the variation is not accounted by our regression model. So that's the way to look at it. And but we have one more term in this context called as the adjusted r squared. Right? We have the term called adjusted r squared, a small modification on the top of r squared. Why is this adjusted r squared required? What it has been observed is, when I keep adding more and more variables, right now let's say we had two variables, two independent variables. Now let's say I add the third, fourth variable, so on. What it is observed is, r squared, because it's a positive quantity, r squared will always keep going up. If not going up, it will be flat, but it cannot come down even if you add the third or fourth or fifth or 100th variable. So r squared will keep increasing only with the addition of variables. This is one point which you have to keep in mind. R squared will continue to keep increasing only with the addition of a new variable. Though even if that new variable does not contribute significantly to the model, the r squared will keep increasing only. If you just want a confirmation, let's say when I have looked at the simple regression model, we got r squared as 0.6372. Okay, the data was slightly different. Here we had 100 observations, here we had 97. But yeah, whatever, even if I do, just to showcase that, probably if I do the regression only removing the assets, only looking at the sales, right? If I do the regression on this data only with respect to the sales and don't include the assets, let me take one more. Now if we see the regression, r squared was around 63.61, whereas when I had added the asset, it has become 63.71. So what we are saying is, even though the new variable does not have any kind of an impact, the r squared will keep increasing only. Otherwise, at the max it may not change, but it will never come down. So people will have an impression that as we are adding more and more variables, the explainability of the set of independent variables on the dependent variable is increasing, so the regression model is becoming more and more better. But what we have to understand is that new variable may not have any kind of contribution to the original variable. So to understand that aspect, is the new variable really contributing anything statistically significant to the model, or is it is the r squared increasing just because another variable got added? These are two things that needs to be looked at. R squared has gone up, fine. So what analysts say is this could be because of two reasons: a new variable added and the variable really contributed. The new variable really contributed something to the variant, to the explanation of the variation in the dependent variable. Now, this is immaterial. Just because a new variable is added, I don't want my r squared to typically go up. So from that dimension, this adjusted r squared as a tool has been brought out to remove the impact of the number of independent variables. If I adjust the r squared to remove the impact of number of independent variables, so remove the impact of number of independent variables from the r squared and call that as adjusted r squared. So for that they have come out with a simple formula. Adjusted r squared will come out as, you take the r squared 1 minus r squared, whichever is the unexplained portion of the variance. That unexplained portion you multiply it with n minus 1 divided by n minus k minus 1, means adjusting it for number of independent. See, the unexplained variation, you are adjusting it by multiplying with total degrees of freedom and dividing it by the residual degrees of freedom. Whatever the value that is coming out, so this is the updated unexplained variation. This is the updated unexplained variation percentage. You do a 1 minus of it, this becomes the adjusted explained variation percentage. That is what comes out as RA squared. So depending on if K is very large, probably the multiplication factor is very high, means if the independent variables are very large, the multiplication factor will be very high. If the number of independent variables are smaller, the adjustment factor may not be that big. So as more and more independent variables are added, there will be a significant difference between RA squared and R squared. So in reality, what is said is, don't look at R squared for our analysis. Better focus on adjusted R squared. So what is that we said? The first step, do 1 minus R squared. Okay, 1 minus R squared. Multiply this by n minus 1. N minus 1 is 96, the total degrees of freedom. N minus 6 is 96, total degrees of freedom, divided by the residual degrees of freedom. So this is this part. And this is the updated unexplained portion of the variant. Do a 1 minus of this, and that is what will come out as the adjusted R squared, which has been shown here. So that is the adjusted R squared. But few interesting things about this adjusted R squared. This is always less than or equal to R squared, or generally less than only. This is always less than adjusted R squared is always less than the R squared, and it may so happen that with the addition of variables, the R squared can keep increasing, but it might possible that RA squared can keep decreasing also. Just to showcase this, you see here, when we did it with one variable, the R squared was 63.61 and adjusted R squared was 63.23. Whereas when I have added one more variable, the adjusted R squared came to 62.94. Means though the R squared has increased with the addition of a new variable, the adjusted R squared had actually come down from 63.23 to 62.94. So which means the new variable whichever I have added here has no kind of impact on the dependent variable. So RA squared has that kind of a power. Though R squared is increasing, RA squared is decreasing. So that means that particular variable is not adding anything statistically significant to the model. It's better that that variable can be removed. That kind of a decision cannot come by the usage of R squared, but it can definitely come by the usage of adjusted R squared. And one more thing is, because it's a kind of adjustment to the multiplication factor, it is very much possible that by definition adjusted R squared can even go less than 0. If R squared is very close to 0, R squared cannot be a negative number, but adjusted R squared, because of subtractions being done, there is a possibility of adjusted R squared being negative also. We have to be slightly careful about it, because in general people think because it's a squared quantity it can never be negative. But remember, R squared is a direct squared quantity, but adjusted R squared is some kind of subtractions and arithmetic being done on the R squared, so it can very well have a negative value also. Especially if the R squared is very, very low, and if the number of independent variables is very high, there is a good chance that adjusted R squared can go negative. So one more thing out of this table, this is the ANOVA table, which explains, which indicates the relationship between the regression sum of squares, residual sum of squares, taking it to whether the model is statistically significant overall or not. Now, this significance which is shown here is similar to a p-value. The significance that is shown is similar to a p-value, which is the lowest significance level, level where the null hypothesis can be rejected. So at a significance level of that and above, the null hypothesis is rejected. So we are talking about a 5% significance. So the null hypothesis is definitely rejected at this point. And what is the null hypothesis in this case? There is no difference between the regression and residual. The variation that is explained by regression is same as variation explained by residual. Alternate says no, there is a difference in the variation that is explained by regression versus residual. So whenever I have this significance value less than 0.05 or 5%, I will reject the null and I will go with the alternates and make a conclusion that the regression model is able to explain the variation in the dependent variable quite comfortably. So regression model is much better than a random scenario or a gut feel kind of a scenario. So the regression model in this case is explaining the variation in the dependent variable quite comfortably. And one more thing is, this we have already seen, how do we compute the mean sum of square. The total sum of squares divided by their corresponding residual, by their corresponding degrees of freedom will give me the mean sum of squares. So out of this mean sum of squares, take the square root. Take the square root of this mean sum of squares. That is what you are going to get as the standard error of the estimate. So that is one more relationship that we need to be comfortable with by looking at the ANOVA table. So the standard error, now you see here, when there was only one variable, the standard error of the estimate was 170.96. But when I added one more, it has become 171. So basically the error is increasing with the addition of a new variable, which means the addition of new variable is of no use because it's even increasing the error of the estimate. So we have to look at not just the r squared, but from multiple dimensions we have to look at before thinking whether that particular value, whether that particular variable that we have added is making anything more good to the model or not. Now the next thing I would like to look at in this context is the concept of dummy variables. Especially if we look at the data which we have analyzed till now, profit, sales, assets, these are all quantitative data, right? Scale based quantitative data. But what if one of my independent variables is a categorical data? So if I want to analyze based on one of the independent variables as a categorical data, so probably here, just to add a flavor, what I would like to look at is some of the companies I would like to identify as a big and probably some of them as moderate. So here I would like to classify, I would like to give a classification of small, medium and big kind of companies, right? So these are the three categories, probably from here up to here I would like to put them as big, right? And so these companies, I would like to call them as big. Just for analysis, I am trying to do. So there is a categorically, I am giving some kind of categories. That company set I am calling as big. This I am calling them as, let's say, moderate, and rest all, let's say, I am calling them as small. So, and I want to see, is the relationship between profit, sales and assets anyway different for the size, is different based on the size of the companies. So, which means I am bringing the size of the company as an independent variable into the analysis. How do I bring that size as a part of the independent variable? Alright, so for that, let me shift from here onwards. Let me insert new columns and shift the cells to the right. Alright, here, this is where we talk about the concept of dummy variable. Dummy variable is a variable which always takes binary values only. The values here, just like these values, for a dummy variable, we will always have the values as only 0 and 1. So we have to construct our categories in such a way that this is either 0 or 1 only. It takes the values either 0 or 1 only. So assume that I am creating a variable called big. This is how we create our dummy variable. Let's say I am creating a variable called big. So wherever the company is a big company, it will take 1. Wherever the company is a big company, it will take 1. And for everything else, it will take 0. So this is how we create dummy variables. Then I also create a variable called medium. Wherever it is a medium, it will take 1, else it will take zeros. So because this is a medium company, from here it is taking a value of 1. Right, probably we can decide, probably let me say that I'll take let me take up to here. Let me take up to here as medium, just for instead of keeping it only up to here, let me take even up to here as medium size companies, just for analysis. Rest all we are taking them as zeros. So now I don't need to create any variable for small. This is one more thing, especially when we are working with dummy variables. If we have 3 categories that we need to look at, then it's sufficient that I create 2 dummy variables itself, because wherever it is 0 for both dummy variables, whatever is left over, it is a small itself. So I really should not, it's not desirable, it's not even to do with desiring. I should not use n variables as dummy variables, especially when I am having n categories. Only n minus 1 dummy variables need to be used in the context. So now with these dummy variables, I can recreate the regression relation. Just that if I want to see, is there any impact or relationship between the profit, sales and assets? Is there any improvisation that is possible if if I am able to identify or link up with the size of the variable? So from that context we are trying to look at it. So I will take the data analysis regression. This time the regression I am performing is not just with C column, the independent variables I am taking C, D, E and F, which are sales, assets, big and medium. So let me see how the regression is coming out. Here R squared came to 65 and adjusted R squared slightly improved 63.52, and we are seeing that these are the coefficients. These are the coefficients for sales. This is the coefficient for assets. This for big, the coefficient is 89.34. How do I interpret this? For big companies, a 1 rupee change in sale is a 1 rupee for a big company, the profits are $89 more compared to the other set of companies. Keeping all others compared to the other companies, for a big company the profits are more by around $89. Similarly, for a medium company the profits are less by around $40, keeping ignoring the average. Basically look at it like the difference in the profits between big and all others is 89. Means the big companies typically have around $89 more profit on an average compared to others. So the same way, but one thing we are seeing is that P values are 0.97 and 0.95. The corresponding P values are 33% and 34%, which is saying that these values are not statistically significant. So I cannot derive any kind of conclusions from that. But what we are trying to understand is how do I interpret in case they had been really statistically significant. If these P values would have been less than 5%, I could have made a statement saying, yeah, big companies do make more profits compared to the small and medium companies. It is a very good statement to make. Right? Big companies make a profit of around $90 more compared to the medium and small size companies, keeping in mind the sales and assets are more or less the same. So that kind of interpretation can very well be made in case these values had been statistically significant. So we could have if a new company, let's assume now a new company with some sales and some assets, and let's say it's a medium company, it's under a medium category. Then if I have to predict the sales, if I have to predict the profitability for that kind of a company, I am taking it as intercept plus sales coefficient times the sales number plus assets coefficient times the asset number, and big, it's not a big company, so 89 will not be impacted, but medium coefficient times 1 means if it had not been a medium company, then its profit would have been 40 more. Because it's a medium company, its profit is coming down by 40, so I'm directly putting up a number of 52. Had it been a small company, these two will be zeros. Had it been a small company, even this number would not exist. And if it had been a small company, the profit would have been around 92. And because it's a medium company, the profit has come down to 52. So that is what is being indicated by this model. Of course, though this coefficient is 40, that's because the standard error is around 42 and the p value is much greater than 0.34, my null hypothesis says that this number is not significant at all. So it's as good as a 0. This is also as good as a 0 because the standard error is 91 and the p value is 0.33. This is where you have to really be careful. When it comes to sales, though the coefficient is only 0.12, the p value is saying this value is significant. This coefficient is really significant, means it's not you cannot take it as 0. It's not equivalent to 0. Whereas when it comes here, it's very clear because the p-values are greater than 0.05. It's very clear that I cannot go with the alternate hypothesis here. I am forced to go with the null, saying these coefficients are zeros only. So these values are not statistically significant at all. So I cannot say that for big companies $89 will increase in the profit, or for medium companies $40 is the decrease in the profit. Those kind of conclusions cannot be made because of the p-value, or even that p-value lies between minus 1.98 to plus 1.98, or the other way is 95% interval contains a 0. For all these, the 95% interval contains a 0. Only for this one, the 95% interval does not contain a 0, which means only this value is statistically significant at 95% confidence level or 5% significance level. All these coefficients are not statistically significant, so we can very well ignore these variables. That is what we get out of the analysis. And the most important thing in this particular analysis is how do I understand a dummy variable, especially if there are categorical variables as a part of my regression analysis. How do I take those categorical variables, and how do I use them as a part of the regression equation? That happens through this dummy variable kind of a process. Now we will move on to few important aspects, especially in terms of the issues that could come up, right? Issues that could come up with multiple regression. There are a few additional things. Okay, once we have determined the regression equation and all that stuff, some key things that we need to look at as a part of issues of the multiple regression. Out of that, I would like to start off with the concept of heteroskedasticity. Right, so we'll see what it means, how we can identify it, and how we can typically work around with heteroskedasticity using our data itself. So when we talk about heteroskedasticity, the meaning is, when I say skedasticity, it is more to do with variance. So heteroskedasticity is changing variance. Homoskedasticity is variance is constant. So what we are saying is, as per the regression concept, whether it is simple or multiple, one of the major assumptions of that concept is variance of the residuals is constant across observations. Variance of the residuals is almost constant across the observations. Now, what we may see is, for some set of observations, probably if we see that for some set of observations the variance is going to be very large, whereas for some other set of observations the variance is going to be very small, and if that is unconditional, means there is no pattern with respect to where the variance is high and where the variance is low, we call it as unconditional heteroskedasticity. So there is no linkage between the independent variable and and the variance of the residuals. If there is a kind of relationship between the independent variable and the variance of the residual, that is where we call it as conditional heteroskedasticity. If, let's say, the independent variable is increasing, let's say as the sales is increasing, right, as the sales is increasing, if I see that the error is increasing or error squared is increasing. So this is where we talk about the presence of conditional heteroskedasticity, which is a serious problem that needs to be understood from a multiple regression. Every multiple regression has to be tested for the presence of conditional heteroskedasticity in the data. The simple way of trying out is, generally speaking, the error term should not be correlated in any way with the independent variable. But if I am seeing that the error term is following some kind of pattern with an independent variable, that is where we call it as a conditional heteroskedastic scenario. Now let's say I have a regression equation like this. So let's say some of the points which I have, especially for lower values of x versus higher values of x. Now if I am seeing here, the variation is much smaller. Whereas as the x is increasing, the variation has gone up from the regression equation quite heavily. Because of this is a situation called as conditional heteroskedastic situation. The reason being, there is some pattern with respect to the independent variable. As the independent variable is increasing, I am observing that the way the error term is also increasing accordingly. So there is some kind of relevance and resemblance associated with the independent variable and the error term. So conditional heteroskedasticity is this kind of a scenario which has to be addressed. Otherwise what could happen is, though these regression coefficients are not affected, these regression coefficients, heteroskedasticity does not have any kind of impact on these regression coefficients, but it will definitely have a major impact on the standard error. Sometimes this can be very high or sometimes it can be very low also, because of the presence of conditional heteroskedasticity. So that means it will have a big impact on the t values. If it has an impact on the t value, probably if the standard error is low, the t value becomes much higher, that the null hypothesis will get rejected. Whereas in reality it should not be rejected. Or if the standard error is high, it may so happen that the t value will be much lesser. So in that case there is a possibility that instead of rejecting the null hypothesis, we may not be able to reject the null hypothesis. So because of all these things, even the goodness of fit of the model also will get badly impacted. So all these things have to be kept in mind before we actually use this regression analysis for our prediction purposes. I need to check whether any kind of conditional heteroskedasticity is present in the data. For that, how do I detect? Detecting conditional heteroskedasticity can be done by two mechanisms. One is you just do a residual plot, wherein you take the independent variable on the x-axis one at a time. You take independent variable on the x-axis and you take the error squared, or probably a simple error itself, the residual itself, not the error square. You take the error on the y-axis and try plotting the graph. If you see some kind of pattern among the observations, then probably it's an indication that conditional heteroskedasticity is present in the data. Let me try out. In this data itself, okay, if I have to go with, okay, these are my predicted and these are my error based on the first scenario. right? When I took only the sales and the assets, this were the predicted value and this was the error. So let me do one thing. Let me not include these two things here. So what I can do is I'll take sales as the independent variable and error on the y-axis, and I'll take a scatter plot, right? Okay, I will insert a scatter plot here. So for that I will furnish it with this data. On the x-axis I will take the independent variable, let's say sales. On the x-axis I am taking the independent variable, which is the sales, and on the y-axis I am taking the error. This is one way to check from the graphical mechanism whether there is any kind of conditional heteroskedasticity that is present. Okay, this is the graph that got, so like that I can do it with the second independent variable also. So with this first independent variable taking x, now here there is not too much of a pattern saying as x is increasing the error is increasing or vice versa. We are not seeing much of such kind of pattern. But if such kind of a pattern is, sometimes it may not be easy to detect from a graphical figure also. So that's where sometimes we use a statistical mechanism also to test out. The same way you can try out, instead of taking the sales, you can take the assets and see as the assets are increasing, is the error increasing or decreasing kind of scenario. So this is one way, a graphical way of detecting whether conditional heteroskedasticity is present. As the independent variable is increasing, right, there is some possibility also, because as the independent variable is increasing, we are seeing some huge errors coming up. But of course here also we have some kind of error. But if the pattern is more or less evidently visible, then we can very well say from this graph that conditional heteroskedasticity is present in the data. Whereas the other way which people look at the presence of conditional heteroskedasticity is through a mechanism called Bruch-Pagan test. Bruch-Pagan test. So this is a statistical way of detecting whether conditional heteroskedasticity is present or not. So this is a new regression model, and in this regression model we take the squared of the errors on the y-axis, or it is taken as the dependent variable. Error squared is taken as a dependent variable and independent variable is taken as the independent variable, and a regression is plotted. So let's do that part and then we'll get into the analysis part. So there is to test out statistically whether conditional heteroskedasticity is present in the data or not, we come up with a simple regression model taking error squared. This is the error squared. I will take error squared on the x-axis, on the y-axis as a dependent variable, and error squared as a independent variable, and the independent variable as the independent variable itself. So let me go ahead with the regression part. Right, in this regression I am taking the dependent variable as the error squared. This is the dependent variable, and I will take only one independent variable, let's say sales. Like that I should try out with all the independent variables. Okay, I have taken an independent variable So or probably I can take all the independent variables also together. It really doesn't matter. Okay, let me take instead of one, let me take even the second independent, because that was created only using these two independent variables. Now, when I am taking this, okay, the r squared is coming out to 0.31. In this particular analysis, the r squared is coming out to 0.31. This r squared, not from the original regression equation. I should look at the r squared that is coming through this Bruch-Pagan, through this regression of the squared of the residuals on the independent variables. So in this case, okay, let me take the r squared is 0.3147. Right, I got r squared is 0.3147. What the Bruch-Pagan test says is, you test it as a chi-square test, wherein the chi-square value is nothing but n times the r squared. The r squared which came through this kind of a regression. N is the number of sample size which you have used. So here the chi-squared value through this process, the chi-squared value is nothing but n, which is the total number of records. The total number of records n is 96 times r squared. What is r squared? This one. The total number of records times r squared is what is the chi-squared value for the Bruch-Pagan tests. That is a Bruch-Pagan test chi-squared, where you are multiplying the r squared which has obtained through the regression of squared residuals on the independent variables. That r squared is multiplied by the number of observations. So that is the Bruch-Pagan chi-squared value. You compare it with the critical value. What is the critical value? You compare it with k degrees of freedom. For the data, the degrees of freedom is 95. Or probably for the data, the k degrees of freedom, which is the regression, number of independent variables degrees of freedom. So I am taking chi-squared critical value, assuming k degrees of freedom, which is 2 degrees of freedom. So I take it as chi-squared inverse, wherein I am looking at 5% and 2 degrees of freedom. So the critical value is only somewhere around 0.10. That is the critical value for 2 degrees of freedom. For a 5% level of significance and 2 degrees of freedom. Let me just check. Did I take the value correctly? I think I should use this formula if I am not wrong. 5% and 2 degrees of freedom. Yeah, the value is 5.99, 2 degrees of freedom and 5% level of significance. I am getting a critical value of 5.99. So as long as my computed value is lying between 0 and 5.99, because chi-squared cannot have negative value, as long as the calculated value is lying between 0 and 5.99, I cannot say that there is any evidence of conditional heteroskedasticity in the data. But if I am seeing that my calculated value is beyond this critical value, calculated value is 30, which is above 5.99, so it's a very clear indicator. Here I can reject the null hypothesis, because in this case, in the Bruch-Pagan test, we call it as BP test, Bruch-Pagan test, the null hypothesis is no conditional heteroskedasticity. Whereas the alternate hypothesis says there is conditional heteroskedasticity. So that we are trying to test out by finding out the R squared, wherein residual error squared on the dependent variable and the independent variables. So we take n into R squared, n is the number of observations, and that we are looking at the chi-square test with the number of independent variable degrees of freedom. So based on that we make a conclusion whether conditional heteroskedasticity is present in the data or not. So in this particular data, at least I can say that the conditional heteroskedasticity is present. So how do I correct it? Because my estimates will become quite unrealistic and unreliable. So that needs the correction to that needs some kind of a correction. So based on that, there are two mechanisms. We call it as White's correction, wherein the standard errors get corrected here. We have various mechanisms to modify the standard errors. So once the standard errors are modified, we can update the t values, and based on those t values we can very well again check out for the significance of each of the independent coefficients. And the other way generally, these are going into slightly advanced aspects. We even use generalized least squares mechanism just to make you understand. Generalized least squares mechanism will help us in doing this kind of correction to the conditional heteroskedasticity, which has to be done. So any standardized, any White's correction that we are applying, you will get a modified standard error, and based on the modified standard error we will again redo the testing of the coefficients, and based on that we can arrive at updated conclusions regarding the variables. So any multiple regression kind of scenario needs to be tested out for heteroskedasticity before we are using it for prediction purposes. Then one more issue that can come up with come out with multiple regression is the issue of serial correlation, especially if my multiple regression is more and more associated with a time-based data. There is a possibility of serial correlation. So I'll try to cover this serial correlation related problem when we take up the time series analysis, where the input which we will be taking is a time specific kind of a data. So what we'll do is once we are done with this example, we'll take one more time specific data example, and based on that try to see in that data whether the serial correlation is present, and if at all it is present, how do I address the scenario of serial correlation there. And one more important problem which we see with respect to multiple correlation is the problem of multicollinearity. This we will see now. We'll have another problem of multicollinearity. As a definition, this is nothing but, see, when we talk about independent variables, n number, whatever it is, the meaning is they should be independent of each other. But in most of the cases, what we see is they are mostly interdependent. Probably there is a relationship existing between sales and assets. Logically speaking, both of them need to be independent. And that is the meaning of independent variables. Both of them need to be independent. So there is a possibility that they become more and more interdependent. I can try to express one of the independent variable as a linear combination of other independent variables, which means the basic assumption of regression is getting heavily distorted, and the predictions or the coefficients that we are getting or the estimates that we are getting become more and more heavily unreliable. That is the serious problem associated with the multicollinearity. I really want to know whether my independent variables are really independent or some kind of interdependency exists between them. Because of that multicollinearity, again, standard errors will get inflated. The biggest problem that will come is the standard errors will get inflated. So which means something which should have got rejected for null hypothesis comes out as a conclusion that we cannot reject the null hypothesis, especially if the standard errors are increasing. We know that the t value will go down. T value will go down means it may come within the limits within the limits of plus or minus critical value, which means I may not be able to reject the null hypothesis. So failing to reject the null hypothesis when it has to be rejected, failing to reject the null hypothesis when it has to be rejected is a case of type 2 error. So what we typically see is there is a possibility of a fair amount of type 2 error in this kind of a scenario. Because of heavy multicollinearity, there is a possibility of a heavy amount of type 2 error coming out in the data. So whatever the predictions that we are doing, sometimes if we had to reject the null hypothesis, we may end up not rejecting the null hypothesis and saying that the coefficients are really not statistically significant. So how do we really detect multicollinearity? Of course, one simple way to detect the multicollinearity is look at the p-values of the independent variables. Except this variable, rest all suggest that the coefficients are not statistically significant. Assume for the time being, even this is indicating that it is not statistically significant. If I assume that all the coefficients are not statistically significant, but at the same time my overall goodness of the fitness of the model says statistically significant. So if the p-value here at the ANOVA layer is less than 0.05, but the p-values for all the independent variables are greater than 0.05, that is a possibility of existence of multicollinearity. There is a possibility that the independent variables are really interdependent very heavily. That's the reason no variable is contributing significantly to the dependent variable, but as a combination they are contributing significantly to the dependent variable. So that is a scenario of multicollinearity, where we look at not the independence of the dependent variable, but we are seeing some kind of interdependence between the independent variables. That requires a correction, otherwise our standard errors are going to go up, which may bias the forecast more and more heavily. So we have to make sure that if this is high, if this is having a correlation significance of less than 0.05, all these p-values also should be less than 0.05. Wherever the values are much greater than 0.05, one way of correcting multicollinearity is remove those variables which are not contributing significantly to the model. Remove those variables, one or two of them, and again repeat the model. But sometimes that may not be the case, that may not work in all the cases. Sometimes we may have to depend on procedures like principal component analysis, factor analysis kind of mechanisms to club these various independent variables into lesser number of variables in some kind of combinations, and then use the new variables as the way and use the new combinations of the variables as the input for the regression equation. But one simple way that is suggested, especially when there is a multicollinearity kind of a scenario, is you omit the independent variables which are not statistically significant, but the overall model is statistically significant. Then you can omit one or more of these independent variables, rerun the test, and again look out for the presence of multicollinearity in that. And a few more important points to look at as far as multiple correlation is concerned is there are some common issues, common problems or common pitfalls or common checkpoints that are necessary when we are working out with the multiple regression. Sometimes it may so happen that I omit some of the important variables. So my model may not be that accurate or dependable. If at all I am omitting some of the important variables. In some cases, the variable in its original form may not be contributing to the dependent variable, but doing some kind of transformation on it. See, instead of taking the sales as it is or assets as it is, probably if I do some kind of transformation on the assets, like perform a logarithm on the assets, just giving an example. So instead of taking the asset numbers as it is, I take some kind of transformation, I take a logarithm on it, I take a square root of it, I take something else on it. So any kind of logarithmic or some kind of non-linear transformation on the variable, and then use the transformed variable as a variable in the regression process. Even that might be possible. And sometimes I may have to use a lagged independent variable. Like when I am trying to find out profits versus the sales or something, instead of taking the profits and sales both of the same period, it may so happen that I take the profit of this period, whereas the sales I take of the last period. Based on the sales of the last period, if I say the profits of the current period will be dependent. These are called as lagged variables. Sometimes if I want to find out the stock price relationship between stock price and the profit of the company, depending on the profit in the previous quarter, the stock price in the current quarter could be changed. So these kind of variables where the dependent variable is lagged by one period, even that kind of regression models have to be tried out, and elimination of multicollinearity have to be looked at, and so many other time series kind of specifications, especially varying with respect to the time, I may have to look out for all those things. So because if I am not specifying the model correctly, the regression coefficients can get badly impacted, the standard error can get badly impacted, which could have an impact on the hypothesis testing that we are performing, and the final prediction that we are making also becomes more and more unreliable. So we have to make sure that whatever the estimators we are coming up with, they are completely reliable, and they don't go with a lot of unreliability. Especially sometimes it may so happen that when I try to forecast based on the past data, I may not get the relevant results, because as per the time changes, the input variable is changing quite drastically, and because of all these reasons the model may become more and more unreliable also. So we have to make sure that the model which we are using is more and more reliable and realistic, without too many pitfalls associated with it, because the selection of the model becomes the most important input for deciding the accuracy or for deciding the reliability of the prediction. Now, till now, whatever we have looked at is the scenario where the dependent variable was a scale variable like profit. It was a quantitative variable. But in some cases, we have dependent variables as qualitative variables. Qualitative variables as dependent, like, okay, do I need to give a loan to a person or not? Yes or no. Or categories, right? Group the participants into group 1, 2, 3 based on the characteristics. Group the customers into high, medium, low based on some series of characteristics. So the dependent variable is more of a qualitative dependent variable. See, if we had a qualitative or categorical independent variable, we had used the concept of dummy variables. But if the dependent variable itself is a qualitative or a subjective or a categorical kind of a variable, we cannot use a normal regression model for that. We have various other mechanisms. We call it as a logistic regression model, or sometimes we even use the terms like probit and logit models. All these kind of models, they are applicable to if my dependent variable is a qualitative variable. Even we have a mechanism called discriminant analysis, which can use logistic regression kind of a process. Especially as an example, if I said, do I need to give a loan to this person or not? Will this person default on the loan or not? Should he be treated as a good customer or a default customer? For doing such kind of analysis where the dependent variable is a categorical or binary kind of a variable, we will use separately. We cannot use this regular regression procedure. We may have to use different concepts like discriminant analysis, logistic regression, probit and logit analysis, which I would not be covering as a part of this session, but just wanted to give a flavor of, in case my dependent variable is a categorical variable, what should I do? Can I use the same regression procedure, or is it something else that I need to look at? And finally, just to quickly summarize any regression model, first look at if there is any kind of misspecification in the model. If at all there is any kind of misspecification, look out for a new model. But if there is no misspecification, look out for the individual coefficients. The way you can summarize the model, look out for independent coefficients. If the coefficients, all of them are statistically significant, either through the p-value, all the p-values less than 0.05 or t-values outside the limits, and look out for the overall model. When all of them are really statistically significant, we can proceed further. Otherwise, to start with itself, I can remove all these independent variables which are not statistically significant and again repeat the model. Now, assuming that all these variables are statistically significant, then I am checking out whether the heteroskedasticity is present in the data. I can check out either with plotting the residuals on the independent variables, or taking the regression between the squared of the residuals and the independent variables. So I can go with whether the heteroskedasticity is present. If it is present, I can remove the heteroskedasticity. The same way I will check out, especially when there is a time specific data, I will check out whether the serial correlation is present. If it is present, I will do the correction for that. I will also check out whether multicollinearity is present in the data. If it is present, even the adjustments will be done for that multicollinearity by removing one or more variables which are not impacting the model that drastically. And finally, I will end up using the model. This is what, in a nutshell, we do as a part of multiple regression process. But of course, in this process, I did not cover the process of serial correlation, which I would be doing when we are taking up the example of a time series kind of a data. I hope you are comfortable with the understanding of the concept of multiple regression and how we can use it as a part of our prediction process. If you have any further queries regarding this, you can very well get back to me by giving me a call on the number that I have provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.